The Materials World modules are hands-on, inquiry and design-based curriculum units for middle and high school students. Using principles from the interdisciplinary fields of materials science and nanotechnology, this curriculum aligns well with STEM objectives, engages students, and adds relevance to existing curriculum.
Hi, my name is William Weber. I'm a teacher at Rufus King High School in Physics and Integrated Science. And today I'd like to talk to you about one of the modules that I co-authored for MWM called Sports Materials. One of the things that makes sports very interesting is the fact that sports is continuously evolving. I'd like to first of all show this by taking a look at some of the balls here to show the differences in details in the composition of the balls. If you take a look at this ball right over here, this ball of course is a typical golf wiffle ball. What makes it unique is the fact that this ball has, of course, an extremely shiny surface with a high degree of pores. One of the things that I would ask my students, for example, in this module is what effect do you think pores would have on, of course, the passage of the ball? How far would it travel? How fast would it get there? These are some of the issues I think that, of course, are addressed in this module. Another ball, of course, that looks similar in size to it, but having a different composition is this ball here. This ball has, of course, a composition that is a rather saggy, butylene type material, a rubber composition, and because of that has a different response to different forces. Including in our selection of balls are solid core balls, for example, like this one, and bladder balls that, of course, have a somewhat fuzzy, flexible texture like this one. One of the big granddaddies of them all is this huge softball that has a hard, almost tortoise-like shell to it with an external seam which will have an effect on the aerodynamics of the ball. In addition to that, it has a kind of a spun woven interior, of course, composition. And as I think you can see in the film, that the composition is different as you move from the inside to the outside of the ball. You can see how the core of this ball is rather loosely packed together. And one of the things that I would ask myself, as well as the students, would be this: what effect would different density have on the ball? What effect would mass distribution have on the ball? And what effect could this possibly have on the aerodynamics and the spin of the ball? So you can see one of the interesting things about compositions of the ball is that, in a sense, you're really trying to determine some of the parameters that make a ball successful for a sport. Now this sport here has to depend upon very little distance. And the reason I say that is because the lack of compression of the material in the ball. So as you go from a low density area to the exterior part of this ball, you can see that it's not similar to a hard ball, which would have an extremely tight wrapping, along with, of course, a self-adhesive glue on it. So this ball, as we probably already know, does not give you the carry or the distance. Mark McGuire, for example, would have trouble plummeting this ball over the St. Louis fences 402 feet away, even with those large biceps. Now, some other things that you can see is that what meets the eye is not always, of course, true. For example, here seems to be two pragmatically identical balls. If we held those up to the same height and released them, we can see that the responses are dramatically different. The question is, why is that true? And again, the answer, of course, goes back to the evolution of the ball. There must be something different, inherently interior in these balls. One of these balls is called a happy ball. Can you tell why? The other one, of course, is called the grim, sad ball. And you can see just by the adjectives that are used to describe these balls that they reflect some of the coarse natures of these particular spheres. One of these balls would be good for rapid activity, and the other one, of course, would produce a very dull activity for most people. Inside of here, of course, you have all kinds of other situations. You can see in this particular case that we have a flexible, of course, exterior with an interior that, of course, is composed of compressed air. One of the things that's interesting is as you go through the evolution of balls for sports, some of them have solid cores, and some of them, of course, do not. So the question becomes to my students, and hopefully to yours, what would compressibility of air have to do with some things like the response of the ball? So another factor that I think that would be important for teachers to know is the fact that as these balls begin to tire because of use and abuse, that the pressure in these balls, of course, is released through the pores of the rubber. And so one of the things that we want to teach our kids is the fact that although these balls are made of materials and they seem solid by nature, they are truly elastic and mostly air. So this cover, as we look at it atomically, is more spatial than it is, of course, composed of material. Hence, of course, the gas that is in here that is actively moving has a chance to exude out of the ball and eventually change, of course, the response of the ball. So many other, of course, balls are used. Here, of course, is an evolution of about 100 years, and this little prized, of course, gem. This is a golf ball with a solid core. And as many people already know, that this one, of course, has lots of space materials on it. The exterior, of course, core of this ball is made out of Surlyn material, which is an extremely strong resinous material, an isomer. And coupled with that, of course, you have a extremely wonderful geometric patterning of the dimples. One of the things that's going on currently in golf technology is the issue of how to space and orient these particular dimples. As it turns out that more and more research is showing that the current dimple pattern in the ball is becoming, shall we say, extinct. That better distance can be achieved by a diamond pattern instead of the hexagonal pattern that's currently on this ball. So as Titleist, of course, evolves their balls, and other companies are evolving their balls for greater distance or touch or feel or rotation, the important thing to realize is that you have to build and evolve your materials for, of course, the demand of the sport. Each sport, of course, utilizes certain criteria, but almost all sports depend upon durability. And so in this particular case, this ball is an extremely durable ball because, of course, of the Surlyn cover, whereas other balls, for example, may not be as durable in the sense of this wiffle ball, but because of the equal balanced structure of the ball, of having the same pressure inside and outside, this ball is allowed to survive many, many hits. So one of the points that we want to make is that this ball here was purposely designed, just like this ball here was purposely designed. Every ball evolves for a function. And so one of the things that we're going to learn in this module is that by looking at simple variables and simple parameters in a laboratory environment and asking, of course, the right questions, that we can, of course, develop the basis behind the evolution of these balls. One of the things we learned in the last part of the module was the fact that the composition of the ball has an effect on, of course, the properties of the ball. One test, of course, that is used in all sports is the test called the Coefficient of Restitution. It sounds like it's a pretty difficult concept. I mean, when you use terms like coefficient and restitution, especially for middle school and high school, but don't let it shake you. Coefficient is just simply a number, and it's used, of course, throughout science. The way I tell my kids not to be scared of this is to simply say that coefficient is a number, just like using a sun blocker. You take a look at a sunblock and it's 15, and it's just a number that represents something about its capability. And so what we have here is a number that, of course, is generated by a very, very simple test that can be done in almost any environment. It's called a rebound test. What we like to do in the second part of this activity is demonstrate this by using, of course, a certain device. This can be done in the classroom, of course, with a meter stick or with tapes that are basically measured off. And what you would do, of course, is provide, of course, a background for the elevation of the ball and also its rebound height. Now remember, this is just a ratio or a fraction between the release height and the rebound height. So I always tell my students that when using a ball like this one here, that when you release it, make sure your environment is clear. And you take it, you release it at this point, and then of course you catch it at this point. And when you slide this over to the meter stick, or in this case to the measuring rod, you can see that the rebound height over here is not identical to the drop height over here. So mathematically, to find the coefficient of restitution is very simple. I take this height divided by the original drop distance height and take the square root of it, that magical little radical key on the calculator, and the end result is I get a COR. It's called a coefficient of restitution. Now every sport has one. That's the miraculous thing. I can remember as a little boy playing golf for the first time with a ball that didn't look much like that, but it did look rounder like this. And when I took this ball, I remember my dad, of course, going to the ball cleaner. I said, "What are you cleaning that ball for?" He said, "You got to get the dimples clean." I said, "Why is that?" He said, "Well, that affects the flight of the ball." And I was kind of like stunned. How could a little dirt, for example, on the dimples of the ball affect the flight of the ball? The second thing he did was even more interesting to me. He took the ball and raised it, of course, to his head, and then he began to proceed to drop it. He let it hit on the concrete, kick back up, and he took the ball with the highest rebound height. I turned around to him, and of course, not knowing coefficient of restitution, I asked him what he was doing. He said, "What I always do is take the ball that has the biggest kick, because that gives me the biggest roll, the biggest, of course, drive, and everything else." So there was dynamical and physics reasons for taking the ball with a big kick. One of the great things about the sports module is the fact that you can really hook your students on it. One of the first things that you'll notice when kids come into a classroom is sports. Kids talk sports. And one thing you can do is finally integrate, in particular, mathematics and science into sports. For example, these units have closure on such mathematical fields as graphing, the use of calculators, the use, of course, of equations and equation studies, and, of course, the end result, developing some of the important parameters and variables in sports science. Another great thing about this is developing the observation skills. Kids get a chance for the first time to look at things in both a large and small plane and begin to see differences that really account for something. And if we're going to try to make great scientists, I think we have to develop that skill as well. Beyond all that, of course, is links with all kinds of other fields. Balls are made out of different materials, and materials are made out of atoms and molecules, and they traverse just about any field that you can think of. And beyond that, too, is the idea that these things link together to produce mysterious things like polymers that really develop, of course, the concepts of chemistry. When I look at, of course, this module, I see it a lot more than just a sports module. I see it a chance, of course, for kids to discover, to invent, to ask questions, and to take a look at things in greater depth than normal. And, of course, it's not just static like sometimes some of the classroom activities are. This gives a chance for cooperative learning and, of course, complements people working together to generate answers. And the beauty of this is that the answers, of course, are not known. And sometimes the answers are quite discrepant. So when students, of course, pick up this manual and they begin, of course, to take a look at the sports materials module, they understand that the process learning that they're getting is both iterative and constructive. And this makes for a very strong classroom learning environment. I recommend for teachers around the country that are trying to parallel some of the content of the curriculum, of course, and standards in their states as well as the nation, that this thing, of course, does a wonderful job of complementing them and meeting them at the highest level. The module, of course, matches many of the science and math standards and gives the opportunities for free expression and creative learning for your students.